So let's now. Okay, so welcome back everyone, and we are going to have Pavel Etingof from MIT, and he will tell us about algebra and representation theory without language. Please.
Yes, thank you very much. So this is joint work with Kevin Coulembier and Victor Ostrik. And so if there is a problem with sound or questions, please let me know. Just speak, unmute yourself and speak. So I would like to start with application. So this is about some new theory of representations, Lie theory and algebra in tensor categories. But to motivate this subject, I would like to start with an application. So let G be a finite group and P be a prime, where the interesting case is when P divides the order of the group. And so let V be a finite this group over some algebraically closed field K. And the interesting case is when the field has positive characteristic. And characteristic divides the order of the group. And so I'm going to study the following invariant of this representation. So we will consider the sequence Dn of V, which is the number of indecomposable summands of V to the nth power of dimension coprime to P. So in general, it is interesting to take a representation to a power and decompose and look. So by the Krull-Schmidt theorem, there is a unique decomposition into indecomposables, and then count them and study the behavior of the corresponding sequence. But this is difficult, and we cannot say much about that. So we will study this problem of indecomposables of dimensions coprime to P. This turns out to be more tractable. So what can we say about this sequence just from elementary viewpoint? So we can, well, one thing is clear that it is super multiplicative, which means dn m plus n of V is bigger or equal dn of V and times dm of V. And also dn of V, so this is because if you tensor two powers, V to the n and V to the m, and pick a summand of dimension coprime to P in each of them, then the tensor product of those summands will contain at least one summand also of dimension coprime to P. So that explains this inequality. And of course, we have another trivial inequality, which is the dn of V is at most dimension of V to the n, which is because dn of V is obviously less than or equal than the dimension of the V to the n, because every indecomposable summand is at least one dimensional. And now to define the invariant I want, I will recall a lemma from elementary analysis, which is called the Fekete lemma. And it is often used in the theory of tensor categories, Grothendieck rings, and so on, green rings. It says that if you have a sequence of positive numbers, which is super multiplicative, then if it is bounded by an exponential function, then it has a root of degree n of a sub n has a limit, which is a positive real number. And so we can define, in our case, this limit d of p, which is the limit when n goes to infinity, dn of v to the power 1 over n, which is a non-negative real number. Well, if a n's are 0, for example, it is going to be 0. Otherwise, it will be a positive number. And so, this is the invariant I want. And so this means that I attach the real number to every representation. Well, this has some obvious properties, which are easy to see. First of all, that the gross dimension of the sum is greater or equal than sum of dimensions. Gross dimension of the product is greater or equal than the product of gross dimensions. So this is obvious because, for example, for the product, again, if you have b to the n and w to the n, and you take an indecomposable in b to the n and indecomposable in w to the n of dimension coprime to p, and tensor them together, you get a representation of dimension coprime to p. So it has at least one summand coprime to p. Well, so all of these inequalities are shown in this way. Also, if dimension, well, there is one stupid case when the dimension d of x is 0, and this is when all indecomposable summands have dimension divisible by p. So it turns out that if you have a representation indecomposable of dimension divisible by p, this is called a negligible representation. And it is not difficult to show, and well known in modular representation theory, that if you tensor such a representation with another one, then all summands you will get will also have dimension divisible by p. They all also will be negligible. And so if all summands in x have dimension divisible by p, then it is negligible, and d of x is going to be 0. All the dn of x will be 0. Otherwise, it is positive, and in this case, it is at least 1. Well, clearly, because all our numbers are at least 1, and at most dimension of x. So this is actually all you can say just from elementary considerations. For example, it is not clear at all from elementary point of view if the number d of x is algebraic or transcendental. And if we were counting representations of different kinds, for example, non-projective summands, which is what people like to do, we do not know up to this day whether this representation is algebraic or transcendental. But in this case of non-negligible representations, we actually know that it is algebraic and of a very specific form. More specifically, we have the following theorem, which we proved with Coulembier and Ostrik 3 years ago, and it's published in the Annals of Mathematics. And the theorem says the following, that first of all, this function d of a representation extends to a character of the split Grothendieck ring, also called the green ring of this category of representations. So this is a ring in which basis is formed by classes of indecomposable representations, and multiplication is just tensor product, and decomposing into indecomposables. So this means that the inequalities here are actually equalities. These inequalities here actually turn out to be equalities. D of v plus w equals to d of v plus d of w, and d of v tensor w equals to d of v times d of w. And the second statement says what kind of numbers we get from such homomorphism. So let q be a root of unity e to the pi I over p, and m sub q is the q analog of the number m, which is q to the m minus q to the minus m over q minus q inverse. So this is this sum. And then for every x in the representations of G, d of x is actually a linear combination of these numbers with positive integer coefficients, non-negative integer coefficients, where m runs between 1 and p over 2. So in particular, if p equal 2 or 3, this p over 2 is less than 2, and so m has to be 1. And so this is a linear combination of ones with non-negative integer coefficients, which means just a non-negative integer. So d of x is an integer in this case, not just a, I mean, we didn't know whether it was algebraic and transcendental, but actually it is an integer. And for p equal 5, actually it doesn't have to be an integer. So let me give you an example what happens in that case. So the simplest example for p equal 5, which is interesting, is the group G equals to z mod 5. And we will take, so indecomposable representations of this group are Jordan blocks. So the group is generated by element G with G to the 5th equal 1. And in characteristic 5, this equation can be written as G minus 1 to the 5th equals to 0. So indecomposable representations of this group in characteristic 5 are given by Jordan blocks of sizes 1, 2, 3, 4, and 5. And those will be denoted by J1, J2, J3, J4, J5. And I'm going to start with representation J3. So this is the three-dimensional representation, which sends the generator of Z mod 5, which I'm going to realize as the additive group of F5, into the matrix here, which is a 3x3 unipotent Jordan block. So then it is easy to show that if you raise v to power n, you're only going to get summands with odd size. So J1, which is just the one-dimensional matrix with 1, J3, and J5. And this follows from the fact that we have the following tensor product rules. So if you multiply v with J1, so J3 with J1, this is just J3, obviously. If you multiply v by J3, this can be decomposed. Well, when I say equal, this means isomorphic or conjugate. J1 plus J3 plus J5. And v times J5 is actually, so this is the same, the Clebsch-Gordon rule, which is what happens in characteristic 0. But when you tensor with J5, J5 is a projective free module over the group algebra. And so when you tensor a projective with any representation, you get a projective. So that means in this case, just 3. So it has to be 3 times J5, which is different from characteristic 0, where you get J3 plus J5 plus J7. But in this case, we don't have a J7. And so when you reduce from characteristic 0 to characteristic 5, J3 plus J7 gets glued into 2 copies of J5. And so what you get then from these rules, well, first of all, you see that you never get any even Jordan blocks. And also you get some recursions for these AN, BN, and CN. So what you get is, first of all, that AN plus 1 equals to BN. Well, because if you tensor this with B, the only way to get J1 in the decomposition is get tensor J3 with J3. So AN plus 1 will be obtained from BN. So AN plus 1 equals to BN. So AN equal BN minus 1. Also, similarly, BN plus 1 equals to AN plus BN. Well, that's because when you tensor, you want to get J3. There are 2 ways to do so, when you tensor J1 and when you tensor J3. And so that gives you BN plus 1 equals to AN plus BN. And substituting the first equation into the second, we obtain BN plus 1 equals to BN plus BN minus 1, which is the Fibonacci recursion. And in fact, this means that dn of v is an plus bn, which means we are only counting representations of dimension not divisible by 5. And this is bn plus 1. So this is a Fibonacci number. And this implies we know that Fibonacci numbers grow like geometric progression with denominator 1 plus square root of 5 over 2, the golden ratio. And so d of v equals to 1 plus square root of 5 over 2, which happens to be 2 sub q, where q is the 10th root of unity. And then in general, our theorem says that in characteristic 5, this d of x for any representation of any group will be of the form r plus s times the golden ratio, where r and s are non-negative integers. And I should say that the same theorem is true much more generally. It holds for any affine group scheme or super scheme over K. Okay, so now I'm going to explain the proof of this theorem, which is based on the theory of tensor categories. But before that, I want to see if there are any questions, and also to confirm that you can hear me well.
Yes, all good.
Okay, any questions?
Can you hear us?
No question?
There's a question. Can you hear us?
Yes, yes. No, but now I cannot hear.
Oh,
You
didn't speak.
No questions.
No questions?
No.
All right. Okay, so let me explain the proof or ideas of the proof. And for this, I need to recall the notion of a symmetric tensor category. So it's a category which has the structures and properties of a category of finite dimensional representations of a group. So let me just review these properties. So first of all, it needs to be K linear abelian over some field K, which I'm going to assume algebraically closed. Then it needs to be Artinian, which means that objects have finite length and home spaces are finite dimensional. But actually, this condition is going to be superfluous if we make some assumptions below, will follow from other. Then there is a monoidal structure, which means that we have a tensor product functor, associativity isomorphism, satisfying pentagon relation, and unit object. Then it needs to be symmetric, which means that the tensor product is symmetrical. So there is a braiding, symmetrical braiding S CXY, such that it is, if you do it twice, you get the identity, and also it should satisfy two hexagon relations, left-handed and right-handed hexagon relation. The category should also be rigid, which means that there is a functor of J-king duals, which satisfies rigidity axioms. And so these are axioms of the additive structure. This is axioms of the multiplicative structure. And then, of course, we need some connection between them. So we should say that tensor product is bilinear on morphisms, and also that endomorphisms of the unit object is K. So actually, if you make this assumption, endomorphism of 1 is K, and that objects have finite length, this actually implies this assumption. And so what are examples of this? Well, this was the definition is given on the basis of the example of a finite group, or more generally, a finite group scheme over K, category of representations. So this is definitely an example. And the most basic case is when the group is trivial, when we get the category of vector spaces over K. And then this is not the only thing that can happen. There is a very simple example that doesn't belong to this class, and that's the category of supervector spaces, which exists when the characteristic is not equal to 2. So as a monoidal category and as an additive category, it is completely the same as a category of Z mod 2 graded vector spaces, which is the same as category of representations of the group Z mod 2, because we are in odd characteristic. So this is just spaces V, which are decomposed as V0 plus V1 with the corresponding tensor product rule. And the only difference is that, well, that category, if we put the usual symmetry on this category, which is just the flip, we would obtain, of course, a category of this type when G is Z mod 2. But we take a different commutativity isomorphism CXY, which sends X tensor Y for homogeneous vectors X and Y to Y tensor X multiplied by the sign, -1 to the degree of X times degree of Y, where the degree is this subscript here. So this means that X and Y should be either from V0 or from V1. So this means that this is the same as usual, except one case, when both X and Y belong to V1, in which case we have to put a minus. And this makes this category different from the previous one, so it's not very difficult to show. But once we have that example, we can generalize it by considering, so symmetric tensor categories are nice because you can do in them whatever you can do in ordinary algebra. So you can consider algebras, modules, Lie algebras, algebraic groups, group schemes, and so on. And in particular, we consider affine group schemes internal to the category of supervector spaces, which are called affine supergroup schemes. So this just means that we take some. So what is an affine group scheme? It's a spectrum of a commutative Hopf algebra. And in a similar way, here we should take a commutative Hopf algebra, but in this tensor category. So we have a natural notion of commutative algebra in a tensor category. And then you can take representation category of this G. So a typical example is the group GLMN of automorphisms of the superspace of superdimension Mn. And we can take representation categories, so that would be interesting tensor categories. But actually, we want to do something slightly more general, which is the following, that suppose you have an element in your group, supergroup. So this is the points of, so supergroup scheme, well, you can think of it as an spectrum of a Hopf algebra, but another way to think about it, similarly to usual group schemes, is as a Grothendieck functor of points. So for every commutative algebra, in this case, in our category, in the category of supervector spaces, you have points of G over this algebra, which is just a usual group. And this is just home from O of G to this algebra. And in particular, you can consider points over a field K. So that's an ordinary group. And suppose we have an element there which squares to the identity. And the conjugation action of this element on function algebra is by parity automorphism. So this means that on the 0 part of this, it acts by 1, and on the 1 part of this, it acts by minus. And then you can consider representations of GZ, which is the category of representations of G on supervector spaces, such that Z acts by the parity automorphism. So that's slightly more general than the previous example. And so these are the examples. So now we're going to need a notion of tensor functor between symmetric tensor categories. So what does it mean? So it's basically it's a functor that preserves all structures. So it should be exact. which means it should preserve the additive structure, and it should preserve the tensor structure, which means it should be equipped with a tensor structure map JXY. It's a functorial isomorphism between f of x tensor f of y and f of x tensor y, which satisfy some compatibility relation. And the tensor functor from a symmetric tensor category to the category of vector spaces is called the fiber functor. So this comes from topology, where people consider categories of locally constant sheaves on topological spaces. And in this case, fiber functor can be obtained by taking fiber of a local system or locally constant sheaf at a point of this topological space. And the definition is the following, that the symmetric tensor category is called Tanakian if it admits a fiber functor to vector spaces. So Deligne and Mill showed that in this case, this functor is unique up to an isomorphism, although non-unique isomorphism. But in any case, you can define a group in this case, which is a tensor automorphism group of this functor. So that's actually not just a group; it's an affine group scheme in just usual affine group scheme, which as a functor of points is defined by the formula that its points over a commutative algebra A is the group of tensor automorphisms of the functor f tensor A. So this is f with scalars extended to A. So that's a functor from our category C to the category of A modules. Well, you can also define the algebra of functions on G. This is so-called co-end of the functor f, which is just the topological dual of the endomorphism algebra of f. So endomorphism algebra is a topological algebra. It has a topology of inverse limit, because endomorphisms of f is the inverse limit of endomorphisms of f of x for all objects x. And so we can take the dual of this, and that's going to be co-end f. So that's a co-algebra, but it also has a natural algebra structure, which makes it a Hopf algebra. And the category C is the category equivalent to the category of representations of the group G. So this is this statement is called the Tanakian formalism. And then there is a version of this, a super version of this, when characteristic of K is not equal to 2, which is goes under the name of super Tanakian formalism. So the definition here is that the symmetric tensor category is super Tanakian if there is a fiber functor, but in this case into super vector spaces. And everything generalizes. So in this case, f is also unique. And we can define G, which is the group of tensor automorphisms of f, which is an affine supergroup scheme over K. This G has a canonical element Z, which is the parity automorphism, because every f of x is a superspace, so it has a canonical parity automorphism. And C it can be identified with representations of G, comma Z. So every such category can be uniquely represented in this way, where G and Z are unique after conjugation. And this is the so-called super Tanakian formalism. Now, you might ask whether we have any other examples of symmetric tensor categories. And it turns out that they do exist. There are so-called Deligne categories, which can be obtained by interpolating classical representation categories, such as representations of symmetric group or general linear group with respect to rank, where you make the rank n into a complex number. But these categories are kind of wildly behaved. They are tensor powers of an object grow very fast in this case. They are not bounded by an exponential function. So this motivates the following definition due to Deligne. So symmetric tensor category C has moderate growth if for every object x there exists a constant such that the length of tensor power x to the n is less than or equal to cx to the n. So lengths of tensor powers are exponentially bounded. So, for example, if X is a representation of a group or a supergroup, then this is true, and you can take this constant to be the dimension of X over the ground field. Now, the Deligne categories, as I said, are not of moderate growth. These are interpolations of representations of GLN. But if you impose moderate growth condition, then over a field of characteristic 0, it's remarkable theorem of Deligne that this is all you can get. So the theorem says that a symmetric tensor category over a field of characteristic 0 is super Tanakian, if and only if it has moderate growth. And the key fact is that this theorem, it's an amazing theorem, but it's rather deep and beautiful, but it doesn't hold in characteristic P. And the fact is that it doesn't hold in characteristic P is actually not a bug, but a feature which enables this new Lie theory, and which actually will enable us to prove this theorem about modular representations that I stated at the beginning. So, I'm going to discuss now how exactly this theorem fails, and how this can be used how this can be corrected, and how it can be used to prove our theorem. But before this, are there any questions? And also, please confirm if there is good sound.
We hear you fine.
Okay. All right. So for this purpose, we will need the notion of semi-simplification of a symmetric tensor category, which is the following. So it's actually this notion is known for tensor categories which are not symmetric, but only pivotal or spherical. But we will use this notion for symmetric tensor categories. So given an additive we can do it in a more general setting when our category is not abelian. So if you have a rigid symmetric monoidal category C over field K with endomorphisms of 1 equal K, then first of all, we have a notion of trace of a morphism. So this notion is central in theory of tensor categories, topological field theory, because it's used to obtain invariance of knots and 3 manifolds. And so the notion is the following. You take, so if you have an object X, well, first of all, I said that all objects are rigid, which means that they come with evaluation and co-evaluation morphisms. Co-evaluation morphism goes from 1 to X tensor X dual, and evaluation morphism goes from X dual tensor X to 1. And then, so I take the co-evaluation morphism, and then I act by my endomorphism F on the first component. So I go to X tensor X dual. Then I take the braiding map to switch X dual to go to X dual tensor X. And then I use the evaluation morphism back to 1. So the composition of this morphisms is a morphism from 1 to 1 which is, according to this assumption, just a number in K, and that's called the trace of F. And in particular, an important example is when F is the identity, then we obtain a scalar, which is called the categorical dimension of X, which is a number in K. For example, in the category of representations of a group, this is just the usual dimension, but regarded as a number in the field K. And if it is a supergroup, then this is the super dimension, which is the even dimension of the even part minus the dimension of the odd part, but again regarded as an element of the ground field. And so now we need a notion of negligible morphism. So I mentioned already negligible representations, but there are also negligible morphisms. So a morphism F between two objects X and Y is called negligible if for every morphism the other way, from Y to X, the trace of the composition equals to 0. And note it doesn't matter in what order you compose, because trace of FG equals to trace of GF. And so the first lemma that we will need, that negligible morphisms form what is called a tensor ideal, N and C. So what is a tensor ideal? This is a collection of subspaces N of X, Y in home spaces, home of X, Y, for every X and Y, such that it is closed under composition with any morphism on any side, and also under tensor product with any morphism. And so when you have a tensor ideal N in a category C, monoidal category C, you can define a new category C mod N, which I call C bar, and it is defined as follows. Its objects are the same as C, but morphisms in C bar from X to Y is morphisms in C from X to Y modulo N of X, Y. So that if N is a tensor ideal, then this will be a monoidal category. So in particular, we can do it in the case when N is the ideal of negligible morphisms. And the second lemma that I'm going to need is the following. Assume that the trace of any nilpotent endomorphism in C is 0. So you may have never seen an example when this doesn't hold, but it doesn't always hold, although it can fail only in rather pathological situations. For example, if your category admits a monoidal functor, even non-exact one, just additive one, into abelian category, abelian tensor category, then this will be true. Because in an abelian category, an nilpotent endomorphism admits a filtration by kernels of powers of these endomorphisms. And it's upper triangular, strictly upper triangular with respect to this filtration. So it's easy to show that its trace must be 0. In a non-abelian category, the notion of kernel isn't defined. And so in fact, the property can fail, but it usually holds in most situations. And so then this quotient C bar, which is C mod N, turns out to be also a symmetric tensor category, which is not just abelian, but also semi-simple. So, here we finally will need a third lemma, which is due to Dave Benson, which allows us to describe, well, to prove that this category is semi-simple and describe its simple objects. So the lemma says that though Benson proved it more than 40 years ago in the setting of modular representation theory, when the theory of tensor category wasn't yet a thing. But it holds in that generality. So under the above assumption of trace of nilpotent morphism is 0, you have the following description of when a morphism is negligible. Well, actually, it's better to describe when it is not negligible. The lemma says that if x and y are indecomposable, then f is not negligible if and only if it is an isomorphism and dimension of x is not 0. And also, if you have a morphism within arbitrary objects, which decompose into indecomposables like so, then for this morphism to be negligible, it is necessary and sufficient that all matrix coefficients Fij are negligible for all I and j. So that lemma is not very difficult to prove. Its proof is based on the fact that endomorphism algebras of indecomposable objects are local finite dimensional algebras, which have the form your field K plus M, where M is the maximal ideal, and this ideal coincides with the nil radical of your algebra. And the corollary of this lemma is that simple objects in this category C bar are the indecomposables of C of non-zero dimension. So every indecomposable in C gives rise to a simple object in C bar, except those which have dimension 0, and because they will become 0. So this is very easy to see. So you take the endomorphism algebra of your object. Like I said, it's local, so it is K plus M, where M is your nil radical. So M gets killed in the semi-simplification because it's nilpotent. So what remains is K. However, that only is true when dimension is not 0. If dimension is 0, then the K also gets killed because trace of the identity is the dimension, which is 0. So this means it's negligible. And so the entire object becomes 0. So, well, this is in a way a bad news, because this means that this category C bar, on one hand, it is simpler than C because it is semi-simple, which C is not. But on the other hand, it is more complicated than C because classification of indecomposable objects is usually a wild problem which cannot be solved. For example, if you have a P group in characteristic P, as simple as just ZP cross ZP for odd P, you cannot enumerate indecomposable objects. However, the irreducible objects are very simple. It's just the trivial representation. But indecomposables are very difficult. So category becomes semi-simple, but the price to pay is that you will get a lot of indecomposables. So this category is called semi-simplification. And let's consider an example what happens in the case of representations of Z mod P. So this is a kind of a rare case when the situation is so simple that we can classify indecomposables. As I mentioned, that they are just Jordan blocks J1 through JP of sizes 1 through P. And so in the semi-simplification, the simple objects are going to be L1 through LP minus 1, which come from J1 through JP minus 1. But JP is going to get killed because it has dimension P, which is in characteristic P is 0. And the tensor product is given by the so-called Verlinde rule, which we see also in conformal field theory and the theory of quantum groups. So it looks like Kleb-Jordan. So if M and N are small compared to P, this is the usual Clebsch-Gordon rule for SL2 representations. And if we didn't have this P minus M and P minus N here, then it would be the usual Clebsch-Gordon rule. But it is actually a truncated version of that. And so for this purpose, for this reason, this category C bar has been named Verlinde category and denoted by ver P, even though, of course, Verlinde, he wrote physics papers in the 80s where this multiplication rule was discussed, but he never considered characteristic P, of course. And in fact, this category was discovered by Kazhdan and Sergei Gelfand in early 90s, and also by Georgiev and Mathieu, and independently. And actually, there is a category attached to every simple algebraic group, and this is the simplest one attached to SL2. So more precisely, this is just a semi-simplification of the category of tilting modules for the corresponding algebraic group. So that's another way to obtain this category. And another variant how to obtain this category, we can replace the group Z mod P by the additive group GA, by the Frobenius kernel in the additive group GA. So that will give you the same category. And so what is the structure of this category ver P? Well, it's a category ver P plus, has subcategory ver P plus, which is spanned by the objects Li of odd subscript. And also there is a subcategory spanned by L1 and LP minus 1, which is just a copy of super vector spaces that happens for P bigger than 2. And this is just a product. So ver2 it just has one object, simple object, so just vector spaces over K. ver3 is super vector spaces over K, as easy to show. But the only, so the first non-trivial example is ver5. And so if you take the object L3, it generates the subcategory ver5 plus in it. And if you tensor it with itself, well, remember J3 times J3 equals to J1 plus J3 plus J5, but J5 drops out, so you will just get J1 plus J3, which can be written as X cross X equals to 1 plus X. And so for this reason, we know that the multiplicities of tensor powers are given by Fibonacci numbers in this category. And so this is why it's called the Fibonacci category. And so this category, therefore, has no fiber functor, because if there were such a functor, then by applying this functor to this equation, we would get the dimension of f of x, which is d, would have to satisfy this golden ratio equation, which cannot happen if this is an integer. And so this is an example that shows that the Deline's theorem fails in characteristic phi, because clearly this category has moderate growth. And and the same happens for other p. So actually this construction shows that for every p at least 5, the Deline's theorem fails, but actually it also fails for 2 and 3, but examples of that are non-semi-simple. Now, so what should we do with the Deline's theorem? How can we somehow fix it and salvage it? Well, let's remember what happened in characteristic 0. In characteristic 0, we defined our tensor categories on the basis of example of Tanakian categories, which are representation categories of groups. But then we discovered an example which didn't fall in line, and that was super vector spaces. So it didn't have a fiber functor into vector spaces, which was symmetric. So what we did is we said, okay, that's a new example. So let's make it a target of fiber functors. And then we discovered the notion of a supergroup. And then Deline's theorem tells us that supergroups are the only thing we can have in characteristic 0 if we want to consider categories of moderate growth. So maybe we should do the same thing here, where P doesn't fall into this pattern for P bigger or equal to 5. So let's make it target of a fiber functor and consider categories which fiber over ver P. And so, Ostrik conjectured that actually Deline's theorem is generalized, can be generalized by replacing the supervector spaces by ver P in characteristic P. And he proved this conjecture for fusion categories, which was a remarkable paper in 2015. So he proved that if C is a fusion symmetric tensor category over K, which means it has finitely many simple objects and semi-simple, then there is a fiber functor from C to ver P, and in fact, it is unique. And in this case, the category can be identified with representation category of the affine group scheme of automorphisms of F, compatible to fundamental group, which is a technical point that I'm going to skip. And the G is a finite group scheme in ver P, linearly reductive finite group scheme in ver P. And so the study of such category C reduces to the study of such groups. We now have a conjecture of what these groups look like. And so this will allow us to classify such categories. However, one might ask what happens with categories which are not fusion, but just moderate growth, so not necessarily semi-simple and not necessarily with finitely many simple objects. Well, in this case, there is a counterexample in characteristic 2, which is quite simple. I'm not going to go over it right now. With Benson and Ostrik, we constructed counterexample for all primes bigger than 2. But then we might ask what prevents the category from having a fiber functor to vector Verlinde P, for example, to ver 2, which is vec K. And that's what is called non-exactness of Frobenius functor. So Frobenius functor in characteristic 2 can be defined just as cohomology. Frobenius of X is cohomology of 1 plus C on X tensor X, the kernel of 1 plus C over the image of 1 plus C. And this happens to be non-exact in these counterexamples. It's an additive functor and a monoidal functor, but it is not always exact, turns out. So here explained here, but I will skip it. So if this functor commutes with any monoidal functor, any tensor functor, so if Frobenius is not exact, then we cannot have a tensor functor in a semi-simple category. Because in a semi-simple category, any additive functor is exact, in particular Frobenius. And one can define Frobenius functors for any P. In fact, these functors were a crucial tool for Ostrik when he proved his theorem. So I will skip the definition because it's not going to be important for what I want to, for the punchline. But one says that C is Frobenius exact if this functor is exact. So Frobenius functor for characteristic P, at least one part of it, which is enough to consider it for this theorem, is just Coulombier's Frobenius functor, which is the image of symmetric power into the divided power of X. Symmetric P's power into divided power. So this is the image of co-invariance of SP into X to the P, mapping to the invariance of SP in X to the P. And the main theorem so that we proved with Coulembier and Ostrik, this is in this annals paper, is that the Lin's theorem holds for Frobenius exact categories of moderate growth if you replace supervector spaces with the category ver P. In other words, C is Frobenius exact and moderate growth if and only if there exists a fiber functor into ver P, and in this case, it is unique. So in particular, this holds for semi-simple categories, symmetric tensor categories, because they are, for them, the Frobenius functor is automatically exact. And finally, I'm able to explain how this can be used to prove the theorem about growth for modular representations. For this purpose, we will take our category to be representations of G, where G is, let's say, a finite group, or more generally, a fine group scheme over K. And this category is non-semi-simple in general. So we are going to take its semi-simplification, C bar. And then these numbers dn of x, which is the number of indecomposables in x to the n of dimension coprime to p. Well, it's exactly the length of x bar to the n, where x bar is the image of x in C bar, in the semi-simplification. Because remember, when we define semi-simplification, the indecomposables become simples, except when they have dimension 0, which means dimension divisible by p. So when we do this, then all indecomposables will just become simples, and the ones, except the ones of dimension divisible by p, which will drop out. And that's exactly what this count does. So we get that this is equal to the length of tensor power in this semi-simplified category. And now we will use our main theorem, which says that this semi-simplified category, which is a semi-simple symmetric tensor category, admits a fiber functor into ver P. So, so that means that we can try to compute this length after applying f. Well, it's not the same, this length. So because when you apply a functor which is not fully faithful, this functor is faithful but not full, of course, then length can increase. And it does. But what turns out is that it doesn't increase too much. It increases by a factor that is sub-exponential with respect to n, which means that as long as we're only interested in the asymptotics of root of degree n of the length, it doesn't matter whether we do or don't apply f. So the limit of root n of length x bar to the n is the same as limit of f of x bar to the n. So that's not very difficult to show, and I'm going to skip the proof. But now we are down to computing this limit. But this is a much simpler problem, because that's a computation in our category ver P, which has finitely many simple objects. And in this case, this number is just the Frobenius Perron dimension of this object f of x bar, which is the largest eigenvalue of the matrix of multiplication by f of x bar, and on the Grothendieck ring of this word indicator. For example, if you take object L2, then its matrix of multiplication by L2 in the basis of Li is this matrix, which has ones on the diagonal above and below the main by 1 unit and zeros everywhere else. And it is classical and well known that the largest eigenvalue of this matrix is Q analog of 2, which is Q plus Q inverse, where Q is equal to e to the pi I over P. So this is twice cosine of pi over P. And similarly, lambda of Lm is Q analog of M. And therefore, if you have an object f of x bar, which is the sum of mj times lj, then lambda is going to be the sum of mj times q analog of j. And this implies the theorem from the beginning of the talk, which is that our invariant d of x is an algebraic integer of this particular form. Okay, so I think probably I should stop here. Thank you very much. So I don't know if there are any questions.
Thank you very much. Questions, please.
For your C bar is in simple, but it's not finite in general.
C bar is semi-simple, yes. What is the question?
Not finite. Define it category.
I cannot hear very well. So can you?
Finite category. Does it have finitely many symbols?
No, it is not finite. C bar is not finite. It has infinitely many simples in general.
There are reasonable finite subcategory generated by images of simples.
So can you repeat, please? I'm sorry.
Is there a reasonable finite subcategory generated by images of simples in C bar?
Yes. Well, I mean, you can consider it, but for example, I mean, it might not be interesting. For example, suppose you have a P group. Then every simple object is just trivial, and so this subcategory will be trivial. So you can define it, but it is not always interesting. This problem is very interesting for P groups already, when this subcategory is not very interesting. But it can be interesting. For example, if you take something like GLN over finite field, then this will be an interesting category, because actually tensor product of simples in characteristic P, in characteristic 0, tensor product of simples is semi-simple. But in characteristic P, this is not true. So you will get more.
I remember there are also these categories where P to the N, if I remember correctly. How do they fit into this story? Are they not so much simple?
Yeah.
Or?
Yeah, they're not Frobenius exact. So they do not admit a functor into their P. But again, we might, we hope that actually the Lin's theorem can be, the union of all ver P to the N for a given P, which is called ver P infinity. We hope that every symmetric tensor category in characteristic P admits a fiber functor in ver P infinity. So that's a main conjecture. But we are very far from proving this at the moment.
Any more questions? Not, then let's speak again.
Okay. Any other questions? Yes, there seems to be no further questions.